In this video, we're going to look at how to simplify radical expressions. So this is a little bit tougher than some of the other lessons we've done so far. First, let's talk about the different parts of a radical. You'll notice that we have a number called the index. Now, a lot of times we don't see a number here. It's a small number, kind of like an exponent in the top corner. But if there is one there, it's going to be right in front of the radical, kind of like above where the check mark part starts. If you don't see a number there, then the index is 2. That's kind of the standard square root that we work with. But there are also other roots like cube roots and fourth roots and fifth roots that may come up on an assignment. The radical itself, that check mark looking symbol, this is what helps us separate numbers that are inside of a radical and which numbers are not inside of a radical. And if you ever see the term radicand, that refers specifically to the numbers that are inside. If we have numbers in front of an expression being multiplied, we call those coefficients. Now, I've written up some perfect squares. It's not that I think that these are new for you, but these are helpful to have on hand for some of the steps we'll be doing coming up. Now, this is showing you what happens when you square a number, but squaring and square roots are opposite operations. So it's helpful to look at the purple numbers so that we can recognize what is the square root of that number. So I just want to make sure you guys are able to quickly see a list of those numbers written out, because then it's going to make it a lot easier to say, well, what's the square root of 36? It's just 6 by looking backwards at the blue number. And then the last piece that I have on here, the other definition, it's what are like radicals. This will come up on the adding and subtracting specifically, so I'll come back then. These are radicals that have the same index and the same radicand. So basically, they both have to be square roots, for example, and you can't have a square root of 3 and a square root of 5. Those would not be like radicals. We can only add like radicals, so it'll have to be the same index and radicand for those problems. So 3 root 2 and 5 root 2. It's okay for the coefficients to be different. It's the number inside the square root that has to match, and it's the index that has to match. These don't have an index written, which means it's the index 2 case. So let's look at some of the examples, and I'll come back to this slide occasionally. So first, the easiest process is how do you simplify a radical by itself? Well, try to divide the radicand by any of the perfect squares it is divisible by. My hint to you would be to use the biggest number possible for this. So that's where we'll look back at the table of perfect squares. And then once you've done that, you're going to write the square root of the number you divided by in front of the radical. So we'll bring that number out front like a coefficient. And then if you divided by multiple perfect squares, so maybe you had to do this several times, or maybe there was already a number out front, then all of the numbers that are in front of the radical will need to be multiplied together. So let's look at a couple quick examples. We have the square root of 54. The first thing we want to try and check is what is a perfect square that 54 is divisible by. So if you look back at the table, start with the biggest number possible. It can't be a number bigger than 54 itself, so I'm going to start right about here and say, is 54 divided by 49? No, not as a easily divisible number. What about 36? Still no. 25? No, that doesn't work either. 16? No. But 54 is divisible by 9. So what I'm going to do is I'm going to recognize that since 54 is divisible by 9, then I can think of this as the square root of 9 times 6. And that's helpful because the square root of 9, that's a perfect square. So that means that this is 3 root 6. So that's how I've simplified the radical. You break it down by what are the two numbers being multiplied together, and then you just take the square root of the perfect square number. If you can still simplify the other number, you might need to repeat that process multiple times. But if you used my tip to use the biggest number possible, you should only have to do it once. Here's another quick example. We have the square root of 72. Again, you would refer to the table of perfect squares and try to find a number that it's divisible by. In this case, 72 would be divisible by 36. So I would think of 72 as 36 times 2. 36 is one of the perfect square numbers we looked at a moment ago. And the square root of 36 is 6. So I can break the 6 outside of the radical, which means that this radical simplifies down to be 6 root 2. Okay, now we're going to look at how to add and subtract radicals. So we still need to do that simplifying process. We're going to start off by simplifying any of the individual radicals that we can. And then we're going to look back at the like radicals definition that I shared earlier. So if I go through the simplifying process, the square root of 45, that's 9 times 5. So then the square root of 9 is 3. For the square root of 80, let me write this one out because this one might be a little bit tougher for you guys to recognize. That one is 16 times 5. And then square root of 5 can't be broken down, so I'm going to leave that one as is. So the only one that I wanted to write out for you guys just to make this easier for you to follow, this 16 can be written as a 4. Now I already have a 3 out front, so what I'm going to need to do is multiply the 4 and the 3 together, because both of those numbers are going to be in front of this radical now. So 4 times 3 is 12. So now I have these 3 radicals. So for adding and subtracting, this is where we need to check, are they like radicals? So I'll remind you of the definition we had for this. We said like radicals are radicals that have the same index and the same radicand. Well, these all have an index of 2. None of them have a little number written in the top corner of that square root radical symbol. And they all have a radicand of 5, which means that these are in fact like radicals since the radicands all match. So at this point, I can just kind of ignore the square root of 5, pretend it's like an x. So pretend this says 3x minus 12x plus 4x. Well, 3x minus 12x is negative 9x, plus 4 more is going to be negative 5x. So I'm using x just as a placeholder because sometimes it's easier to think of that as a variable rather than a square root. You guys are pretty comfortable with adding 3x and 5x, etc. Let's do the same thing here for this second example. I'm going to break down these 3 radicals as much as I can first. 32 would be 16 times 2. 162, that would be 81 times 2. And the square root of 98, that would be 49 times 2. So I was able to find a perfect square that all 3 of those numbers are divisible by. Now I can take the perfect squares and bring them out front. So the square root of 16 is 4, but I already have a 2 out front. So 4 times 2 is 8. Next, I have the square root of 81, which is 9. There's no number in front, so it's kind of like there's a 1 in front of this radical. So I just end up with negative 9 root 2. And then the square root of 49 is 7. So I have 7 times the 3 out front, which is 21 root 2. Now again, these do count as like radicals. They are all index of 2. None of them have an index showing. And then that's the most common radical. And then these all have a radicand of 2. So I can think of this as 8x minus 9x, which would be negative 1x, plus 21x, which is 20x, or 20 root 2 in this case. So now let's go on to another one of the operations, multiplying radicals. You still want to do as much simplifying as you can. Sometimes you might be able to break down some of the radicals before you do the actual operations. Then we'll get into how you need to multiply the numbers outside of the radicals together. And separately, you will multiply the numbers inside of the radicals together, the ones we call the radicands. So don't multiply numbers outside of radicals and inside of radicals together. It's only the coefficients get multiplied and the radicands get multiplied separately. And then if we have to, like in a situation where we have 2 terms times 2 terms, don't forget you need to distribute, or some of you might have learned this as FOIL out that product. And then we'll see if there's anything else we can simplify. Again, that might come back up after multiplying the numbers. So starting with the very first case, I can't simplify the square root of 3 here, but I do recognize that 18 is divisible by 9, which is one of our perfect squares. So I can treat this one as 9 times 2. Don't know why the color changed on that. And the square root of 9 is 3, but I do have a 5 out front. So 3 times 5 is 15. Okay? So now let's go ahead and multiply these radicals following the rules I gave you here. Multiply the coefficients, or the numbers outside of the radical, together first. So 2 times 15 is 30. And then multiply the numbers inside of the radicals, the radicands, separately. So the square root of 3 times square root of 2 is the square root of 6. And then see if you are able to do any other simplifying. The square root of 6 does not break down because there's no perfect square that it's divisible by. So that one is finished. Now let's come to another example. Square root of 2, I can't simplify that one. Now the square root of 12, that would be 4 times 3. And I can't simplify the square root of 6. So the first thing I would do is I would rewrite this as 2 root 3. And then I couldn't simplify any of the other radicals. So now this is a situation where we need to remember to distribute. So I actually need to do square root of 2 times this first term, and then square root of 2 times the second term. Remember, we're not multiplying numbers outside of radicals and inside of radicals together. So the 2 is technically being multiplied by an invisible 1. So 1 times 2 is 2. And then square root of 2 times square root of 3, those are both radicands, becomes square root of 6. That's the first part of the distribution. Now I need to do it times the second term. Again, there's an invisible 1 in front of the radical, times negative 4 is negative 4. And then I have square root of 2 times square root of 6 is the square root of 12. Now we just broke down square root of 12. So if I just refer back to my work from earlier, remember that's going to be 4 times 3. So basically I can bring a 2 out of the radical, and then a 3 is going to stay in the radical. So I'm just breaking down that the square root of 12, again, breaks down as 2 times root 3, but I do already have a coefficient out front, so I have to multiply the 2 times the 4 to get 8 root 3. One more example. This one is tougher because I have 2 terms times 2 terms. I don't see any simplifying I can do right now. Square root of 3 and square root of 5, none of those are divisible by any perfect squares. So we're going to go straight into distributing this. So square root of 3 times square root of 3 is the square root of 9. Then square root of 3 times 5 root 5. The 1 gets multiplied out front. So 1 times negative 5 is negative 5. Root 3 times root 5 is root 15. And then I go to the second term in the first binomial here, and I multiply square root of 5 times square root of 3. That's going to be square root of 15. And then square root of 5 times the second term. So I have the 1 times negative 5 out front, and then square root of 5 times square root of 5 is square root of 25. As far as simplifying some of these radicals, well, the square root of 9 is just 3. And I can also simplify that the square root of 25 is 5. So that's going to get multiplied by the other 5 out front and become a 25. I cannot, however, simplify the square root of 15. That's not divisible by a perfect square. So on these, let me leave them as they are for just a second. And then we'll go back to our adding radicals step. So I do have some like radicals here because these are both index 2 and the square root of 15 for the radicand. Also, we can add numbers like 3 and negative 25. So those are just both whole numbers. So 3 minus 25 is negative 22. And then negative 5 root 15 plus 1 root 15 will give me negative 4 root 15. Looking back at the previous example, just to comment on the fact that I didn't add these radicals together, it's because they had different radicands. So remember, you have to have the same number inside of the square root for you to be able to combine them like I did on these two. And now for the last and the most complicated part about working with radicals, it's when you have fractions or when you are dividing with radicals. So you're not allowed to have radicals in the denominator of a fraction. So just like on the other steps, we're still going to try and do as much reducing and dividing as possible. And then there are going to be two cases. There's going to be the case where we just have one square root in the denominator of the fraction, in which case we can just multiply the numerator and denominator by whatever that square root is. So if it's like a square root of 5 in the bottom, multiply the numerator and denominator of your fraction by square root of 5, and then simplify. The more complicated case is when you have two terms in the denominator. So maybe you have something like 2 plus root 3. If that happens, you're going to have to multiply the numerator and denominator by something called the conjugate of the denominator, and then simplify your new expression. So what is a conjugate? If you haven't seen this term before, this is what happens when you have two terms being added or subtracted with at least one of them being a radical in this case. So like maybe you have square root of 2 plus square root of 3. Well, the conjugate just flips the sign in between those two terms. So square root of 2 plus square root of 3 has a conjugate of square root of 2 minus square root of 3. If it had a minus in between the expressions in the first part, then it flips to a positive for the second part. So the only sign you flip is the one in between the two terms. That's the main thing to emphasize for a conjugate. And I'll show you that. It'll be a little bit easier to see with numbers written in, I think. Now first, we have the case where there's just a single term. So this is going to be case 1. There's one radical in the denominator. Now you may still want to simplify this as much as you can first, though. So square root of 4, for example, that's a perfect square. So that's just 2. And the square root of 24, well, that can be broken down as 4 times 6. And the square root of 4 is 2, so that comes out of the radical. If we cancel out the 2's, we just have 1 over root 6. But remember on the last slide I said that we're not allowed to have a square root in the bottom of the fraction. So this is where the step comes in. Multiply the numerator and denominator of the fraction by whatever radical we have in the denominator. Oh, I'm losing my place. There we go. So we're going to multiply the numerator and denominator by that square root of 6. 1 times square root of 6 is the square root of 6. And the denominator, square root of 6 times square root of 6 is 6. That got rid of us having a square root in the bottom of the fraction. That's what we wanted. This one is the tougher case. This is the case where we have two terms with one of them being a radical. So this is now the case 2 situation where I need to multiply the numerator and denominator by the conjugate. So I want to make sure you can see the conjugate carefully. So I have two terms. What I need to do is just change the sign in between the two terms. So that's going to be 5 minus root 3. You need to multiply that on the numerator and denominator, because that way technically we're multiplying by 1, so we're not changing the value of anything. If I distribute this out, I have 6 times 5 is 30, and 6 times root 3 is negative 6 root 3. On the bottom, we're going to need to distribute this, because I have two terms times two terms. So 5 times 5 is 25, and then 5 times negative root 3 is negative 5 root 3. Root 3 times 5 is 5 root 3, and then root 3 times negative root 3 is negative root 9. Now a little hint I'll give you here is that whenever you're multiplying a complex number or a two-term radical expression by its conjugate, the outside and the inside products will always cancel from your FOILing. So if you want, you can just skip that part and just focus on the first product and the last product. So 5 times 5 is 25. Root 3 times negative root 3 is negative root 9. But that only works when you're multiplying a number by its conjugate. Okay, so let's try to simplify what we can here. I have 30 minus 6 root 3 on top. Nothing simplifies there. On the bottom, you might recognize that the square root of 9 is just 3. We know that one. That's a perfect square. So I could do the 25 minus 3 is 22. And then I already told you that these two end up canceling out. So it's just the 22 in the denominator now. The last step is just a rule from simplifying fractions in general. Since all of these whole numbers are divisible by 2, we would want to reduce our answer. So if I divide everything by 2, this becomes 15 minus 3 root 3 over 11. I don't see anything else that the whole numbers are all divisible by, so that's simplified. One more example with the conjugate, the hardest case. So the conjugate of 4 minus root 3 would be 4 plus root 3. You're only changing the sign in the middle. Now I need to multiply these out. This time I'm going to have to FOIL on the numerator and denominator because I have two terms times two terms. So 2 times 4 is 8. 2 times root 3 is 2 root 3. 4 root 3 times 4 is 16 root 3. And then 4 root 3 times root 3 is 4 root 9. On the bottom, let's use that shortcut again. If you're multiplying a number by its conjugate, we only have to do the first and last product. We don't have to do all 4 of them. So the first is 4 times 4. The last is negative root 3 times root 3, which equals negative root 9. Now we will simplify these radicals and fractions to the best of our ability. So the only radicals I see that we can simplify, we know that root 9 is equal to 3. So I could do 8 plus 2 root 3 plus 16 root 3. So 3 is coming outside of the radical, but I do have a 4 there, so 3 times 4 is 12. And then here I'm taking the square root of 9 is 3. There's no number in front already, so it's just the 3 by itself. And now let's try to add and subtract the like radicals. 8 plus 12 is 20. 2 root 3 and 16 root 3, these have the same index and radicand. So that's going to be 18 root 3. 2x plus 16x is 18x. And 16 minus 3 is 13. I don't see any number that all of the whole numbers are divisible by, so we don't need to do any simplifying of the fraction in this case. That was a long lesson. I'm sorry there was a lot to cover there for radicals because there are so many operations and some of this does take so much work. Just be careful on working out your simplifying of the radicals and your dividing and looking for anything that might be able to combine in some way.